Time. It marches forward, an unstoppable force. We experience its passage every second of our lives. But why does it only move in one direction? Why can't we rewind the past or fast forward to the future? This fundamental question has captivated scientists and philosophers for centuries. The answer, it turns out, lies in a concept called entropy. Entropy is a measure of disorder or randomness, and the universe, as it happens, has a penchant for disorder. This journey from order to disorder, from past to future, is what we call the arrow of time. Imagine a pristine, perfectly ordered sandcastle on a beach. Now imagine that same sandcastle after a wave crashes into it, scattering grains of sand in every direction. This, in essence, is entropy at work. The sandcastle, in its ordered state, had low entropy. Once scattered, its entropy increased. This movement from order to disorder is a fundamental principle of the universe. Entropy is all around us. It's the reason your bedroom gets messy, why ice melts in your drink, and why it's easier to scramble an egg than to unscramble it. The tendency of the universe to move towards disorder is enshrined in the second law of thermodynamics. This law states that the total entropy of a closed system can only increase over time. In simpler terms, things tend to become more disordered and random. Heat flows from hot objects to cold objects, never the other way around. Gases disperse to fill their containers, never spontaneously compressing themselves. The second law of thermodynamics is one of the most fundamental laws of physics. It governs the behavior of everything in the universe, from the smallest atoms to the largest galaxies. Let's consider a few everyday examples to illustrate entropy. Imagine adding a splash of cream to your morning coffee. Initially, the cream forms a distinct swirl, a fleeting moment of order, but soon it mixes with the coffee, creating a uniform brown liquid. The entropy of the system has increased. Or think about a glass of ice water. The ice, a structured and ordered form of water, gradually melts, becoming liquid. Again, entropy increases as the system moves from a more ordered state to a less ordered one. These simple examples demonstrate how entropy is woven into the fabric of our daily lives. The concept of entropy extends far beyond our coffee cups and ice water. It shapes the evolution of the entire universe. Stars, powered by nuclear fusion, burn through their fuel, releasing energy and increasing the entropy of the cosmos. Galaxies collide and merge, their once orderly structures spiraling into chaotic beauty. Black holes, those cosmic monsters, devour matter and energy, further increasing the universe's entropy. Even the expansion of the universe itself, the very fabric of space-time stretching outward, can be seen as a consequence of entropy's relentless march. Section 6. The Big Bang, a low entropy beginning. The story of our universe starts with an event so monumental it set everything we know into motion. If the universe is constantly moving towards disorder, what does that tell us about its origins? This relentless march towards chaos, known as entropy, hints at a very different beginning. The prevailing theory, the Big Bang, suggests that the universe began in an incredibly hot, dense, and surprisingly ordered state. Imagine a moment when all matter and energy were compacted into a singular point, a state of perfect order. This low entropy beginning is a puzzle. How did such an ordered state come to be, and why did it explode into the chaotic universe we see today? It's like finding a perfectly built sandcastle in the middle of a hurricane. The contrast between the initial order and the ensuing chaos is stark and thought-provoking. Scientists are still grappling with the implications of this initial low entropy state. They are delving into complex theories and simulations to understand how such a state could have existed and what it means for the future of the universe. But one thing is clear, the universe has been moving towards disorder ever since. From the formation of galaxies to the decay of stars, entropy is the driving force behind the cosmic dance. The Big Bang was the starting pistol, and the race towards maximum entropy is still underway. As we look to the stars, we are reminded of the incredible journey from order to chaos that defines our universe. Section 7. Cosmic timekeepers, stars, galaxies, and black holes. These celestial wonders are not just random objects scattered across the cosmos. They are the very fabric of our universe, each playing a crucial role in the grand cosmic ballet. The universe is filled with celestial objects that serve as markers of time's arrow. From the twinkling stars that dot our night sky to the massive galaxies that span millions of light years, each one tells a story of time and space. Stars, for example, are born, live and die in a predictable sequence. They begin their lives in vast clouds of gas and dust known as nebulae, where gravity pulls the material together to form a new star. As stars age, they go through various stages, eventually ending their lives in spectacular supernova explosions or quietly fading away as white dwarfs. This entire process is driven by the relentless increase of entropy, a fundamental principle that dictates the direction of time and the evolution of the universe. Galaxies, vast collections of stars, gas and dust evolve over billions of years. These colossal structures are the building blocks of the universe, each one containing millions or even billions of stars. Over time, galaxies undergo dramatic changes. Their majestic spiral arms slowly wind tighter as entropy takes hold, and interactions with other galaxies can lead to spectacular mergers and transformations. The spiral arms of galaxies are not just beautiful to look at, they are evidence of the dynamic processes that shape the cosmos. Even black holes, those enigmatic objects from which nothing, not even light, can escape, play a role in the universe's journey towards disorder. These mysterious entities are formed from the remnants of massive stars and have a profound impact on their surroundings. Black holes consume matter and energy, growing ever more massive and influencing the orbits of nearby stars and gas clouds. Their immense gravitational pull can even bend light, creating fascinating phenomena known as gravitational lensing. These cosmic phenomena are not merely beautiful displays, they are testaments to the power of entropy to shape the universe over eons. Each star, galaxy, and black hole is a chapter in the story of the cosmos, a story that continues to unfold with each passing moment. As we gaze up at the night sky, we're reminded of the incredible forces at work, shaping the universe and guiding its evolution. The dance of stars, galaxies, and black holes is a testament to the beauty and complexity of the cosmos, a never-ending journey through time and space. Section 8. Entropy's grip on everyday life. Entropy's influence is not limited to the vastness of space. It governs our daily lives in countless ways. Our bodies, complex and organized systems, are constantly fighting against entropy. We eat food to maintain our structure. We exercise to combat the natural tendency towards decay. Even our thoughts and memories are subject to entropy's grasp. Over time, memories fade, details become muddled, and the past becomes increasingly difficult to recall with clarity. This, too, is a manifestation of the universe's inexorable march towards disorder. Section 9 times arrow, a universal constant. While the concept of entropy and its connection to the arrow of time seems fairly straightforward, there are tantalizing hints that time's arrow may not be as absolute as we once thought. The traditional view holds that time moves in one direction, from the past to the future, driven by the increase of entropy. The world of quantum mechanics, the realm of the very small, is full of strange and counterintuitive phenomena. Particles can exist in multiple states at once, and their behavior can be influenced by observation. Some physicists believe that quantum effects could potentially lead to violations of the second law of thermodynamics, which states that entropy in a closed system always increases. At least on microscopic scales, these quantum anomalies suggest that the arrow of time might not be as rigid as we perceive it in our macroscopic world. Furthermore, the possibility of a multiverse, a vast collection of universes existing alongside our own, throws another wrench into our understanding of time. Each universe could potentially have its own distinct timeline and physical laws. This idea challenges the notion of a single, universal arrow of time and opens up a myriad of possibilities for how time could function differently in other realms. Could time's arrow flow differently in other universes? Could there be places where time moves backward or where it loops in cycles? These are questions that continue to fascinate and challenge physicists, driving them to explore the deepest mysteries of the universe. Pushing the boundaries of our understanding of the cosmos, these inquiries not only deepen our grasp of time, but also of the very fabric of reality itself. The quest to understand time's arrow is far from over, and each discovery brings us closer to unraveling the true nature of time.